Professor Cola has been able to join us, which is awesome. He's a professor of mechanical engineering at Georgia Tech and also founder and CEO of, I have to do this, a totally cool company called Carbice, and has a totally hot talk that he's going to give us today. Sorry about that. But anyway, Bara, please go on.
All right, the double pun. I like it. I like it. Thank you, Ed. Let me share my screen. All right. Thanks for having me here, and thanks for that introduction, Ed. I won't have any slides today. I'm actually just going to use the web. I think because young people use the web a lot on their phones and things. And I want to introduce myself by, if you Google Baratunde Cola and you go to the images, there are images here that span 20 years. So I'm 41, I think. When I was 21, I looked like this big man here with a mustache and a bald head, and I played football. You can see this guy down here. And, here I am at 41 holding a carbon nanotube sample, one that I keep with me. I've had with me for 11 years. And my story is really one of, if you look at these pictures, you look at a student that I advised when I was a MLK visiting professor at MIT, my postdoc who turned into my CTO at Carbice, to my undergrads and high school students here with some STEM outreach, and to one of the undergrads that was in my lab taking, I started a course called Nano Engineered Energy, and Leo here became the third employee at the company, was a student in my class. Then my career and my, impact really has been broad and focused on things that excite me and that just are naturally interesting and fun for me to do, from sports to business to interesting people. And, you see here in the middle, I've given a lot of talks. I've had, through the story of telling the work that I'll get into next, it's giving me these opportunities to interact with a diverse group of brilliant people, to have an opportunity to speak from high school students to senior researchers and so on. And it really all started actually a couple years before I had this thick neck and wore this mustache, because in 1999, I started on an undergraduate program. I actually got a grant through my professor at Vanderbilt. It was an NSF summer undergraduate research supplement that helped introduce me to nanoscale carbon. And at that same time, I was introduced to the trouble with heat transfer, right? So if I move on and we look at like why the area of research for me, which is heat transfer in materials, is such a problem. And it really comes down to a couple of things that if you think about being able to move heat energy off of an electronic device to a heat sink, there are two parameters that are talked about. One is thermal conductivity, which is basically how many highways do you have open to transfer heat from one side to the other. And that's important, and it's an intrinsic material property. And the other is thermal resistance, which you can have many highways open, but how many bridges do you have, right? So when you have bridges that are out, you have high thermal resistance. If all the bridges are closed, you have a low thermal resistance. Simple to explain. I tell people all the time that out of all the heat transfer, you don't need any differential equations or complex math to look at how heat transfers across an interface, because it's really algebra. It's really just simple math. It's the change in temperature and the thickness of a material. And it goes back, however, to a very fundamental scientific problem that first got me into the space. And it was when people were looking at materials, a lot of focus was on the thermal conductivity. And even when, I'm a carbon nanotube researcher, that's kind of one of the things that I've specialized in. Even when people start looking at nanotubes, people spent most of the time looking at the thermal conductivity. But as it turned out, and this was key to my early work in developing measurement tools, metrology, that could actually separate the measurement of thermal resistance from thermal conductivity, we discovered that it was actually the thermal resistance that was the limit to performance in these type of situations. And that's important because it really defined my entire career, right? I tell people all the time, I majored in mechanical engineering and math as an undergrad. And when I went to grad school, that tool set helped me become a metrologist, measuring thermal properties at all types of length scales, finding new resolution to decouple things, right, with math equations. And when we did that, and when I was, one of the first to really identify the components that made up a complete thermal path in an interface, it really set me on this path to carbon nanotubes and why they are great for thermal interface materials. And so if I go here and I look, I want to show you this image because this is an image of a vertically oriented array of carbon nanotubes grown on both sides of aluminum foil. This structure is unique in that it allows you to make very good thermal contact in the interface because of its unique mechanics. And it's the mechanics of this material that we began to focus on once we realized that the key to improvement was contact resistance instead of thermal conductivity. And by focusing on it, we could then say, well, the mechanical problem for this material is the attachment and then the deformation. And so that's what we've looked at. We looked at the deformation. So here's an image of that same array under compression, where we learned and observed that these nanotubes, they undulate and they fold in like springs, which gives them unique elastic potential. So they can be materials that can be compressed and rebound over many cycles, right? And it's at a larger scale here, you're seeing the material and how the nanotubes bend, which taught us about the mechanical contact at the surface. Because at first, people would draw cartoons of very straight nanotubes with tips touching the surface. But when we learned the mechanics, we learned that it's more of a line contact. It's laying on a surface, right? Which dramatically changes the way you look at how heat gets out of the nanotube into a surface. So this fundamental problem, which was one geared towards electronics, how do you get heat out of a data center chip efficiently without using more than all the electricity we already use to cool it, turned into a problem of metrology, of decoupling thermal conductivity from thermal resistance, learning that thermal resistance interface contact was a dominant thing, then figuring out how to understand the mechanics that cause that contact, and then figuring out how to take that understanding and do something useful with it, right? We talk about impact. I started a story with people. People are central to the story, but it's also a story of tech transfer because, this timeline at the top is things in the lab and at the bottom is things in business. That aluminum with CNTs on both sides was first demonstrated in a paper when I was a grad student at Purdue in 2007. I did my PhD dissertation on this topic. One of the centerpieces of the dissertation was looking at the mechanics and really explaining the deformation at the individual nanotube layer and bringing that up to a macro scale. I started as a professor at Georgia Tech in 2009 and had a team working on a DARPA grant called nanothermal interface materials, because it was important And it still remains one of the key issues to system advantages for the defense and satellites and vehicles. And so that work funded our ability to focus on this mechanical problem that was uncovered in my PhD work, where we developed a bunch of novel techniques to address that, one of which is shown here, where if you want to improve the contact of a single nanotube to a surface, it's like a cylinder sitting on a plane, you want to pack some putty or something soft and conformable to expand the width of the line contact. And this is what we did with conformal polymer coatings. We also did conformal metal coatings. So we spent a lot of time, and I built my research group with a lot of grad students and postdocs and undergrads, figuring out how to solve that contact problem, that mechanical problem to the tips. But at the same time, I started Carbice in 2011, 2 years into my faculty career. And it was interesting because the state of Georgia has a program called the Georgia Research Alliance that gave faculty members small grants to explore commercialization. And Craig and I here, we had a grant where it allowed us to start looking at how to scale this and like what applications would work well in industry. Because you have ideas as a researcher, but until you take your ideas and engage with industry, you don't really find solutions. But along that journey, there was another fundamental scientific advance that was required. And that was, we could grow these nanotubes. We could figure out how to put these coatings on that improved how they connected to a surface at their tips. But you needed a way to grow them where they would stay on the aluminum foil. And that was really the key to Carbice, was that we figured out a way to mass produce growing carbon nanotubes vertically on both sides of aluminum and solve a chemical engineering or chemistry problem to get the nanotubes to stick covalently to the metal. And so that enabled a lot of things, right? So we combined that discovery that enables scale up that was supported first by the Georgia Research Alliance, then an SBIR grant in 2012 from the Air Force Research Lab, and then a grant from the Army, and then a grant from the National Science Foundation that went all the way to phase 2, phase 3 for scale up to get us to this point where in 2017, we were able to make this aluminum with CNT structure at 500,000 square inches per year. And up top, the science part of it kept feeding from the lab into the business because we demonstrated a coating approach, but that coating approach, you start to learn fundamental differences between coating a nanotube with a polymer that has a high hardness versus a polymer that is soft and malleable and wets versus a polymer that has a cross-linking capability that doesn't outgas. And that actually led to the product portfolio that this company has. There's a space pad, which is a version of this aluminum foil CNT with a low outgassing NASA compliant polymer coating. Solves the contact problems at both sides, adds a functionality to the customer that was from the discovery in the market. And then we have a product called the contact pad, which is used in semiconductor test, where it has a very hard polymer, but it's still compliant because of the nanotube mechanics. And it's able to go millions of insertions in the making and infant mortality testing of chips without losing performance. And we have another flavor of a wetting polymer that when put in the interface softens almost like a liquid, but the chemistry makes it stick to the nanotube so that it's the only solid pad material that performs just like a liquid in the interface, which is an interesting combination of properties. And so with that, in this journey of Carbice, part of tech transfer is first solving kind of the IP transfer problem, taking basic science that solves a problem, answers a question, turning it into a form where you have something where you can go and run market experiments and figure out what form of that science needs to be presented to different markets. And then 2020, you build a business. You start learning about how these things that you develop from first principle science fit into the application framework of different applications that exist throughout the industry. And so, that's been the story of Carbice, one that started as an undergrad with NSF-funded undergraduate research. It's touched so many people directly through my lab, but also supporters and people around, to the point where this material is now in a facility in Atlanta that is making and capable of making 20 football fields a year of this material. And it's out there. It's the largest production facility of vertically aligned carbon nanotubes in the world that go into real applications, satellites, power modules for electric vehicles. And it started, with a 21-year-old with a thick neck and a mustache doing some undergraduate research at Vanderbilt.
Well, thank you, Bar. That was another fantastic talk. And of course, you weren't able to join us earlier, but we heard another talk from Maya on someone I know or know of, Millie Dresselhaus, on who really created all the fundamental work. Great example of standing on the shoulders of giants before ahead of time. Though I'm tempted to ask you about football, I won't. And I'm also not going to ask you about the other thing, which I know you must get asked about all the time, which is, how is it with the last name Cola, you ended up at a school named after, or not named, well, after a guy who was, of course, on the Coca-Cola board of directors. We won't go there either. But
we don't go into the fact that I grew up in Pensacola either.
And we won't go there either. All good times. But what I'm curious about is how your background prepared you to go from being, a researcher to being an executive and raising money. And, if you see any correlation between the two in terms of having to apply for grants, NSF grants and DARPA grants versus having to go out and get venture capital.
I take hard criticism very well. And that goes from all the grant denials, all the 2 years in review with the high impact journals, the PhD committees. What I find in industry is that people are not made quite as hard as you can be made during the academic life cycle. And so I think that helps me well, because you take hard criticism well, I think it allows you to learn fast and respond fast. And that's key in raising money, because you could present to somebody in the morning and learn something and need to change your presentation for the afternoon. And then I want to point out, because one of the best conversations I had was with Dresselhaus when she visited Purdue back in 2008. This is something to help prepare me to be a CEO and executive, is that I co-founded the Nanotechnology Student Advisory Council at Purdue. I was the first student to move into their Burke Nanotechnology Center, and I was the captain of giving tours to that facility. And so I gave Millie a tour, and we stopped at my presentation and had a long debate about how phonons come out of the tip of CNTs, because it has a hemispherical cap. And I think that I took a position that I later realized that she was right and I was wrong. And it helped influence a lot of the research that I did at Georgia Tech.
That's great. Well, maybe Maya's next book will be on you. But one other question then is, as you've taken the work that you did as a researcher and tried to commercialize it, and this is something I'm always fascinated about, where were you most surprised? And it could be either positively or negatively in terms of what it took to commercialize it. I'm thinking more now about the fundamental engineering, not the raising of money and things like that.
Yeah. Here's the most surprising thing, and it's something that I still look at as a competitive advantage actually today, is that most of the reason, technology is hard to translate it and make products, but it's not as hard actually as getting people to change how they think about things. And the education barrier for deep tech can be high sometimes, and meaning that it's quite surprising, like the way industry gets set up. people don't have to necessarily think so deeply about things to operate and kind of move their organization along, no matter what their level of training is. So when you bring something like a thermal interface material, there will be a lot of what I affectionately call like Carbise wrong thinking. And you can never show up and tell someone about wrong thinking. So you have to figure out ways, like this website that the company built that I use for talks, because it's so informative and it's like an encyclopedia of how this problem is. And those are the things that I would not have anticipated before. I've thought that, you show up, you show someone some data and they would, immediately like get excited, like I get excited. And there's this, and that doesn't happen. Even if the data is like really good, it's like, hey, here's what you have, here's what we have, and look how great it is. And no, it's like you got to start taking, you got to go back to the basics and say the mechanics of this material are different. So you can't put this material in a finite element analysis and ask for the Young's modulus and the Poisson's ratio, because it's not defined in this material. So here's how you look at it. And they say, oops, oh, well, they don't know how to look at it. We built our own software package to look at it, because then you realize that you just need to hand them a new tool that plugs into the way that they do things. So right. I'm still learning. It's a learning journey being someone who runs a company like this.
Yeah, well, we wish you luck.